Hello and welcome to another CS200 mini lecture. This will cover the first part of chapter 19, which discusses searching and sorting. It provides an introduction to what you'll see in a later class, probably CS301. So let's get started with this first mini lecture. If you recall from an earlier definition in the class, an algorithm is a sequence of steps for accomplishing a task. In this mini lecture, we'll talk in more detail about algorithm design and how designing an algorithm can affect things such as the time it takes and the amount of memory it requires. The first topic is linear search. So let's go through this example. So what we have is we're looking for an item. So we're looking for item 14. So we keep going from one end to the other until we find the item we're looking for. So it took 4 steps to find item 14. Now we're looking for 11, which doesn't exist in our array. So what we do is we scan the whole sequence of values in the array from one end to the other. And when we get to the end and we have gone through all the elements and we don't find it, we would return a value saying we didn't find it. It may make sense to use a -1 as a flag to indicate we didn't find it. But let's take a look at the linear search in more detail. So here's the algorithm, and I'm going to take and look at this in BlueJ. Here we have the linear search algorithm, and this is exactly what we found in our Zybook. So we begin by defining a method called linear search, which is going to return an integer. In other words, it's going to return the value that we found. And we're going to pass it in an array of integers. We're going to call that numbers, and then a key. So we're going to specify the values in the array as well as the key that we're looking for. So we have I as a counter. So we say for I equals 0 and to the end of the numbers array, we're going to count and loop through as many times as we need until we find the key. So if we find the key, we're going to return the position that we found it. Otherwise, we're going to return -1, which means we didn't find it. So here's our calling method. And in this calling method, what we do is we declare our array of numbers. An integer I, we have our key and our key index. A key index is going to return going to receive the value. The key index is going to receive the value we return from the linear search algorithm. So first we print out our numbers. Then we loop through, and then we print them out. And then what we do is we prompt the user to enter a value. And then we call this method, passing the numbers array and the key value that they entered to search. And key index is either going to have the position in the array, or it's going to say it was not found by holding a -1. And this is the if statement that says if we find it or not. Obviously, if we return a -1, that means it's not found. Trouble. So let's go ahead and run this. So here we're being asked to prompt to enter a value. I'm going to enter in something that exists. Let's say 32. And I found it in space 5. So let's run it again. This time we're going to put a value in that doesn't exist. I'm going to put in a 44, and it doesn't find it. If we find the value, we can know the position, and that's actually the value that gets returned to our main from the method linear search. And if it's -1, we're just going to print this. By now you are aware that that's not a very efficient way to search for items. There's another way that's better called binary search. So binary search is very similar to what you would do if you're playing hotter, colder, or higher, lower. So in this game, and we saw this at an earlier example earlier in the course, is if I have a number in my head, say the number 44, and I ask you to guess a number between 1 and 100, and I'm going to tell you if you get it, if it's higher or lower. And in this case, your first guess, knowing this information, is to guess a 50. And I'm going to tell you lower, and then you're going to divide that in half and probably guess 25. And then I'm going to tell you higher, and so forth, until you arrive at the number. And this allows you to reduce the search space by half each time you are getting feedback from me, who knows whether the number is higher or lower. Of course, this means that your information has to be in sorted order. The linear search didn't need to be in sorted order because you're just scanning the items one by one until you find it. However, binary search, because we're applying some kind of division in terms of the search space, we need to have it in sorted order. Let's take a look at this example. So in this case, we're looking for the value puja. And we start by looking at something in the middle of the search space, which is the array. In this case, it happens to be Muhammad. We know that P is greater than M in alphabetical order. So what we're going to do is we're going to go up in search values that are higher. And then we're going to keep searching them. So Sharad must be 3/4 the way through the alphabet in terms of what we have to work with. But we know it's less than Sharad and higher than Muhammad. So what we're going to do is we're going to go between the two, and then once we find the middle value there, we either go higher or lower until we find it or we don't find it. This takes far fewer steps than a linear search would in most cases. So let's take a look at the binary search, first through an example, and then we'll go to BlueJ. So in this case, what we're doing is we're trying to find a value. In the first case, it's 16 that we're trying to find. So what we do is we have a way of finding that by declaring a mid value, and we're constantly redefining that mid value as we go along. So in this case, we have 14 as our mid value. You can see it's approximately midway through the array. And again, this is a sorted array. So once we hit 14, and since we're searching for 16, that means we're going to go greater than or to the right. So what happens is we redefine our search space to be between 14 and 63, and we find the mid value, which happens to be 24. We make a comparison against that 16, and we see that it's lower. So then we're going to go to the left, and what we do is we find our value. And once we find our value, that's what we return. We return the key, which is 4, back to the calling method. Here's the search algorithm. Let me go to BlueJ and show you there. So just like we had seen in the example, we have to declare 3 variables, mid, low, and high. And just like the previous example, we're going to return an integer, and we're going to be passed in an array of numbers and a key we're looking for. So initially we set low equal to 0, and the high is the length minus 1. So this is not the actual value. This is the index position. So we will search from the low of 0 and then the length of the numbers array minus 1. And that's our initial search space. So while high is greater than or equal to low, so generally that's going to be the case if we haven't found the value, then mid equals high plus low divided by 2. So what we're doing is we're dividing the search space in half again. And if numbers is less than the key, then we're going to go left. Otherwise, we're going to go right and go for a higher value. And if it's neither less than or greater than, that means we found it, and we're going to return that ID. Otherwise, we get a -1, which is not found. And the rest of our main looks is exactly the same as what we saw with the linear search. So let's go ahead and run this. So here we have our values, and we're going to search for 32, and we found it in 5, just like we saw with the previous linear search. So if we have 44, again, we're not going to find it, and it's going to return a message indicating that. So one thing that might be worthwhile is to compare the two. We already know that in most cases, the binary search is going to be faster. But how many more steps does it take for us to find the values, say value 32? So initially, the linear search is just going to go on in order. And in this case, the binary search is going to only take 3 steps. And at 3 steps, the linear search would not have found it. Now, is the binary search always better? No, because if we were looking for value 2, then the linear search would beat the binary search. What we need is an ability to explain how fast the algorithm will work in some kind of functional notation. We have big O notation to do this. And what it does is it describes the running time of an algorithm with relation to the inputs that we give it. Generally, the size of the search space is important. So we need to have an ability to analyze this information the best possible way. So let's take a look here. So if we have an algorithm that requires 5 plus 13n plus 7n squared, what we're going to find is the big O notation is going to be on the order of those steps, those quadratic. However, we have a couple of rules we want to follow. If the function is a sum of several terms, what we're going to pay attention to is the highest order term. We're not going to worry about the others. The reason for this is because over time, and assuming a large search space, the others are just going to be rounding errors compared to, say, for example, n squared. And the second rule is if the function has a term that is a product of several factors, we're going to just throw out the constants. So that's why we get rid of the 5. We'll see more examples of this in a minute, but just realize these are the rules we need to follow in our big O notation. This chart nicely summarizes the rules for the big O notation. So if we have a constant c, it doesn't matter if we're multiplying or adding. The constant's going to just be a rounding error, so it's ignored. Also, if we have a function multiplied by another function, it's going to be the order of the two that we're going to pay attention to. So here's an illustration of growth rates for different input sizes. We can see that log n, in most cases, we want to have an algorithm that works the fastest, requires the least amount of time. However, there's some exceptions where we don't want that. For example, if we have a cryptographic message and we want to make sure it takes a long time to break that message, then we would want something that takes a long time to run. Now this is a nice chart to allow us to see the relative growth of different computations versus the number of elements. We are charting 1 through 10 on the bottom, or the x-axis, and that's the number of elements. And the number of computations is going to be on our y-axis. With 1, it's going to not depend on the number of elements. So if anything is to the order of 1, it's not going to be respondent to the number of elements. If it's log n, it's slightly worse, but still very manageable. If it's n, it's going to grow just like we would expect. As the number of elements increase, the number of computations increases. Now n times log n is going to be slightly worse than that. So when we get to n squared, you can see that the growth when we get out towards 10 elements or more is really starting to take a lot more time than what we've seen just a minute ago. So if we have 2 to the power of n, it it's so big that it makes all the others almost blend together. So when we do n factorial, it grows so great that all the other ones just blend together as a single line. Next, let's turn our attention to the runtime complexities for different examples. The first one is a constant. In this case, it doesn't depend on how many numbers. We're just comparing two numbers. And each one's going to take say, a fraction of a second to run. It doesn't matter how many numbers we have. If we're just comparing two numbers, it's going to just be very quick. Now, a slightly longer example is a binary search, which we just saw. And that's where we're defining a search space and we're dividing it into half each time we're making a pass. As n increases, the time it takes increases as well, but not as much as a linear search would. Here's our linear search. In this example, we can see that it depends on the number of elements. So if we have 100 elements, it's going to take, on average, 10 times more than if we have 10 elements. And that's what we mean by linear. If it's log linear, and we haven't talked about sort yet, but this is a case where we are trying to sort values doing a merge sort. So we're going to take and break a problem into pieces, and it's slightly longer than a linear search because we're multiplying it by the log, which is much like we saw with the binary search. With quadratic, here's where we're starting to notice the amount of time it takes to do additional steps for different elements. This is a selection sort. A selection sort is slightly worse than a merge sort for small values, and as the number of values increases, the amount of sorting increases as well, and it takes quite a bit longer. The Fibonacci series is going to take a great deal more time as the number of values increases. Normally, we're interested in time complexity, but there's also space complexity to be considered. So time complexity is how long it takes, depending on how much input we get, and space is how much memory the algorithm requires relative to the amount of inputs. This I got from Wikipedia, but here's a bunch of different types of sorting algorithms. We're typically working with arrays, and you can see that they're looking at time complexity in the best case, the average case, and the worst case. The average or the worst case are considerations. It's easy to come up with a best case. In fact, we can kind of fool the algorithm to come up with something that gets our values right away, but this is not very practical. Most people will look at the average complexity as the most important, but there are times when the worst complexity is our biggest concern. If we have limited sort space, it could be that space complexity is our limitation. So let's make a couple of notes about these sorting algorithms. In the best case, you can see that many of them are on the order of a linear search, and some of them are R log n, which means they're going to be more efficient. And some of them are R squared. We have selection sort, and that's the best case. The average case, you can see we have a little bit more variation. The BOGO sort, of course, is our worst case of the average time complexities. And then BOGO is also the worst for the worst case, where it has on the order of infinity. In terms of space complexity, we see most of them are very uniform, and then some are linear. Of course, there's no perfect algorithm for sorting, but we'll talk more about sorting in the second mini lecture. So let's take a look at some different data structures. We have different ways in which we can measure. We can measure across search, insertion, and deletion. And if you remember, we had one situation with an array list, and then we had a linked list. And you can see that when we did an insertion, it depended on where it was in that array list or that linked list, but the linked list was a far better algorithm for when we want to insert towards the beginning. And it didn't make much difference if we wanted to add something towards the end. So we have ways in which we can measure the time it takes to do an insertion, time it takes to do a deletion, and also for indexing. And then also we have space complexity. In 19.4, we want to look at our analysis. And one of the ways is which we can look at is worst case. So we have a operation where we assign our array. That's just a single operation. And in a for loop, we're going to have n operations because we're going to loop from 1 or 0 to n minus 1. So what this means is we are dependent, in this case, on the number of values, or n. As n grows, this is going to take longer to run. So inside of our loop, we're going to perform 2 operations. The worst case is we have to keep going until we maximize our n. We have one final comparison operator, which is again just a constant. So they nicely color-coded here. And how they color-code it gives us an illustration of exactly what we do in our calculation. We have 3 operations that are not dependent on n. In our for loop, we have some that are dependent on n. So we add the values together. And remember, we throw away the constant. And because for n is really dependent on n, we say this is on the order of n. So let's look at another one. In this one, we have these operations which it doesn't depend on how many numbers we're going to go through. It doesn't depend on n. All of these are in the order of 1. These comparisons don't depend on how many values we're going to have in our for loop. But we do have a for loop that is dependent on n. So we have these operations, and this is also on the order of n. Because the for loop dominates the amount of time this is going to take. Let's take a look at a third one. This one, we have n minus 1 iterations, which is just going to be n. So we have another set, and as we go through, you can see that the number increases every time we go through the for loop. So in the end, we have 2 for loops. And because we have 2 for loops and a bunch of other statements that are not so consequential to the number of inputs we have, the 2 for loops are going to dominate. And because each of those are to the order of n, we're going to multiply them, because in the worst case, we're going to go through all the values twice. And this gives us order of n squared. So here is a figure that illustrates what we just went through. You can see that as we go through the loop multiple times, this is nested for loops. You're going to find those are each to the order of n, and it's going to be the order of n squared. If we had 3 nested for loops, for example, that loop from 1 to n, we're going to be to the order of n to the power of 3.